So in this video, I want to talk about another application of first order differential equations to real world phenomenon. And in this video, I want to talk about radioactive decay. So first of all, what is it? Well, in some atoms, well, in all atoms, there is a nucleus. The nucleus is made up of protons and neutrons, all glued together in some interesting way. But sometimes these atomic nuclei are unstable for some reason, and they want to kind of break apart into constituent pieces. This is referred to as radioactive decay. And this is an example of what's called a quantum process. Okay, and like many other quantum processes, there is just a tremendous amount of unpredictability which is present in them. So in particular, if you're given some kind of unstable nucleus, um, you might not be able to know when it will break apart. You might not, you can't in principle predict when it will break apart, just that it will with increasing probability as time moves forward, because it is unstable and wants to be in a more energetically favorable configuration. Okay. um, but even though you can't predict that for an individual nucleus, if you have a whole pile of these in like a radioactive substance, like you have a whole pile of uranium or something like that, then you can make certain statistical statements. For example, there is this concept of half-life, which we'll elaborate on in this video. The half-life of a radioactive substance like uranium or whatever is the time that it takes for half of that substance to decay away through radioactivity. Okay, we'll get into it here, but before we do, I just want to mention that radioactivity is kind of a scary word, and it is associated with some scary phenomena like nuclear fallout and that sort of thing. But it also has a lot of beneficial aspects. In particular, it's very useful in science. There's something called radiocarbon dating, which takes advantage of the half-life of carbon 14. Carbon 14 is an isotope of carbon, which has a half-life of around 5,000 years. And so scientists can use that to measure the age of certain organic compounds that they might find at like archaeological sites and things like that. They find maybe a bone or some char or whatever, some wood, and they can date it using the presence of the carbon 14 that's present in these old pieces of organic material. Another place where it's useful is in medical diagnosis, in particular cancer diagnosis. So if you do have some kind of cancer, sometimes what they will do in order to precisely locate this cancer in your body is they will inject you with a radioactive what's called tracer. And this tracer is some kind of like sugar. It shares some aspects of sugar. It's got glucose involved in there, and this flows through your bloodstream. And cancer cells are notorious for being very, very metabolically aggressive. They will uptake this compound, this radioactive compound, very, very, very quickly, and so you will get this radioactive tracer accumulating at spots in your body where cancer is present. This cancer, this radioactive tracer will decay, and it will emit, it turns out, positrons. So positrons are the antiparticle of electrons. You don't need to know any of this. This is just interesting science. And these positrons will annihilate with electrons and emit light. And this light can be picked up by what's called a PET scan. PET stands for positron emission tomography. And you go into a PET scan machine, which is like this big tube which picks up the light that comes out of these electron positron annihilations. And then they're able to scan your body. Okay, this is the miracle of science and of basic physics. Let me show you what it looks like, what the scan actually looks like. Here it is. This is not me, but I did get this procedure done again in 2012 when I got my cancer diagnosis. I was diagnosed with diffuse large B-cell lymphoma, and I had a PET scan that looked a lot like this. I just pulled this one down from the internet from an article. And you can see all these black splotches all over this person's body. Their body is riddled with cancer. All of these black splotches are places where the radioactive tracer is accumulated, and it's emitting as it decays through radioactive decay. It's emitting positrons, which are annihilated by electrons, which are then picked up by the PET scan. Okay. Now I know. I did not intend for this to be a sad anecdote. Okay, this is not supposed to be sad. This is supposed to be very hopeful. And this is because cancer happens. Cancer is a reality. I'm sure many of you know and have loved ones that have been affected by cancer. But with the help of science and technology, like the ability to detect precisely where in the body this cancer lives, you can do things like obliterate the cancer. Okay, so what I want to say, this is a before and after picture. Okay, here's before, here's after treatment. You see the radical reduction in disease from before and after. And this is exactly the experience that I had. I did a round of chemotherapy. I did a bone marrow transplant. I had a radical reduction in disease, and that's why I'm alive today, because I was very nearly dead because my body was in this state. And if we lived 100 years ago, this is a death sentence. But it no longer is. This is what science can provide to humanity, okay? It's amazing. And of course, the engineers who build, I mean, it's an enormous enterprise, all of this, right? The engineers who build the PET scan tubes with its extraordinarily sophisticated technology, it's all just so awesome, okay? It's all just so incredible. So I don't want this to be a bummer. These are problems which humanity can solve. If we put our brains together and really work at it. And yeah, this is a very hopeful, I hope, message. Okay, anyway, I do want to talk about radioactivity, radioactive decay. And let's see, can I get rid of this, please? No, I don't want to zoom in on it. I want to get rid of it. How do I get rid of it? There we go, delete. All right. So I want to talk about radioactive decay. Phenomenon. And let's denote by m of t. This is going to be the mass of some radioactive stuff. Radioactive substance at time t, of course. Okay, so this mass is fluctuating precisely because it is decaying. Okay, then there is a differential equation that we can write down for this. The differential equation is very much like the exponential growth equation, except here it's going to be an exponential decay equation. And the underlying assumption for this differential equation is that the rate at which this substance is radioactively decaying is proportional to the amount present. So I can write this as dm dt is equal to negative k m. Now, you might be asking yourself, why is there a negative sign there? Well, it's because we like really making clear that this is a negative constant of proportionality. That negative is what suggests that there is decay present. And so we should make the additional condition, we should indicate that k here is in fact a positive quantity. So if k is positive, negative k is negative, okay? And yeah, this is the equation that we have present there. Then we have an initial condition. The initial condition is just a simple statement. We're just going to say that m of 0, the amount of mass, the amount of stuff, radioactive stuff present at time t equals 0 is just going to be labeled by m sub 0, m naught. Okay? Now, none of this is hard. We've solved this equation before. We know the solution. The solution to this equation is therefore m of t is equal to m sub 0 times exp of negative kt. Okay? This is the how much mass there is at any particular time t. Alrighty? And if you need to understand how, if you want to understand how that happened, just look at past videos, because I think I've solved this at least twice now explicitly. Okay, what is half-life? So let's talk about that. Half-life. So we'll denote this by t sub 1/2, like this. And this is the time for half of the material present to decay. Radioactively, of course. Okay, so you might imagine that you have here, let's say that you have a pile of radioactive material, and let's say you have 10 grams of it. Then you wait a half-life. It's maybe, like, you could imagine the half-life is 5 hours. So you wait 5 hours, and what you end up with is 5 grams. Your pile has shrunk to 5 grams. Oh, I should draw that as if it were half the size. So it's smaller. It's 5 grams now. Okay? And then you could wait another half-life, couldn't you? Maybe this way. Oh, what? Hello, what? Maybe you wait another half-life. T sub 1/2 again, and then you have an even smaller thing down here, and this thing is 2.5 grams. Yeah, and if you wait another half-life, you have something like 1.25 grams. So every time you wait a half-life, your pile shrinks by half. Okay. How can we, if we are given the half-life, how can we use that information to, in particular, figure out K? So here's what I want to say. Yeah, I'll just say that we can use T sub 1/2 to find K. Okay, this constant K. Let's do it. Why? Well, because what is M of T sub 1/2? Well, on the one hand, it is half of m naught, right? M naught is the amount present at time t equal to 0. We're going to wait 1 half-life and be left with 1/2 of m naught. Sorry, right? We're going to wait 1 half-life, t sub 1/2, plug that time into m, and the amount that we should get out is m naught over 2. And then, but on the other hand, we have an explicit formula in red here. Look at this formula. We have that explicit formula for m of t. So we can just plug t sub 1/2 into that. And what we get is m naught times exp negative k t sub 1/2. So evidently, because this is equal to that and this is equal to that, they are equal to each other by the transitive property of equality. Okay? So now we're going to solve this equation, this one right here. We're going to solve that. We're going to divide both sides by m naught, so that cancels the m naught from both sides. I'm going to take the log of both sides to kill the exp. So I have log of log of 1/2 is equal to negative k times the half-life. I'm going to multiply both sides by -1. And remember that when you multiply both sides by -1, that has the effect on the log of taking the reciprocal of the argument of the log. So this is equal to log of 2 is equal to k times the half-life. And then finally, we can use this to solve for k. What we learned is that k is equal to the natural log of 2 divided by the half-life. And this is very useful. If you know the half-life, then you know this k that lives in the exponential decay model. Alrighty? Cool. So now let's use this to try to understand a particular situation that we might have. So for example, radioactive tracer is injected into a patient, it has half-life of 6 hours. Okay? So it radioactively decays, and half of it goes away every 6 hours. All right? Also, there's going to be a biological decay. The kidneys, in particular, will flush out some of this radioactive tracer. Kidneys will remove 20% of tracer present every hour. So however much there is present, 20% of it will be flushed out via the kidneys. The kidneys are a fantastic organ that we have to clean our body and rid ourselves of things like radioactive tracers. Okay? All right, let's write down the differential equation. Let's write down the exponential decay equation for this particular situation. The thing that I want to say is that we have two processes happening here at the same time. So it's a little bit more complicated. I don't know why I'm throwing this curveball at you exactly, except it's more realistic, okay? We have two processes happening here. One is the radioactive decay process. The other is a more biological process that's happening in the kidneys. So if we want to measure, let's call N of T the amount of tracer present. Time T. And I won't worry too much about units right now. I'll let you worry about that. So let's let N of T be the amount of tracer at time T. Then we have the following idea that dN dt, okay, is going to be, there's going to be two sort of contributions to dN dt. There's the radioactive decay contribution, and then there's the contribution by the kidneys. So we could write that as a sum of two things. On the one hand, this is going to be negative negative natural log of 2 divided by t sub 1/2, the half-life of this radioactive tracer, times n. And that's one contribution. And then we have another contribution coming from the kidneys, right? The kidneys are removing 20% of the tracer present every hour. So what this means is that this is contributing an additional 0.2. 0.20. 0.20 is 20% times n. So that for every unit of time that passes, 20% of, sorry, when I say unit of time, in this case, of course, I mean hours. That's the units that we're using for time. 20% of the material present is going to go away. That's the reason why I have this additional term. Okay, but this is easily written as negative log 2 over the half-life minus 0.20. Whole thing times n. All I've done is factored out the n, right? But the thing that I want to sorry, I should put a plus sign here, of course, because I factored out the negative sign as well. The thing that I want to emphasize, though, is that this is what's playing the role of our k in this problem, right? This is still an exponential decay problem, but this is what's playing the role of k. Oh, sorry. This is what's playing the role of k right here. Okay, well, we can easily solve this. This is going to be given by the equation N of T is equal to the initial amount present, the initial amount that was injected into the patient, times the a decaying exponential, exp of this new k that we have here, exp of, and I'll write it like this, negative natural log of 2 over the half-life, whatever that is. Oh, and by the way, the half-life we know. I don't know why I'm being weird. it's 6 hours. Okay, plus 0.2 times n. Oh, what? Excuse me, times t, where t is in hours. Okay. So in particular, we could figure out what uh, um, we could figure out how much of this radioactive tracer will be present in the body after, let's say, 3 hours. We simply plug in t equal to 3 into this expression here. I guess we should know, or hopefully we're given, hopefully we know how much of the radioactive tracer we're putting into the patient in the first place, so we know what n naught is. But if we know that, then we can answer lots of different questions. We can, for example, figure out how much tracer will there be in the body after 3 hours, after 6 hours, after 10 hours. And we can see, because this is we have this negative or we have this decaying exponential, that over time it's going to go to 0. Okay, hopefully that made sense. That's a nice little exposition, and you'll certainly have more opportunity to see um, uh, these kinds of problems. Okay, that's enough for now.